1, 2, 1, 2, yes. Alors, le prochain talk sera... So the next talk will be Konstantin and Declan from Intel. And they will talk about IPsec support and offload in DPDK.
Hello, everyone. It's supposed to be 4 of us, actually, but only myself and Declan made it. So, yeah, let's start, I suppose. We've been told that we should be fast. Okay, so IPsec library current status inside DPDK, it was introduced in 1902. It works with different flavors of crypto device that we have right now. It works with pure cryptodev, which is look-aside none. In other words, it works with RT security, with inline crypto, look-aside proto. It's supposed to work with inline protocol type of devices too, but as far as I know, there is no devices in DPDK, no such devices in DPDK right now. So, supposed to work. What features we do support? We support ESP tunnel, ESP transport for both IPv4, IPv6. We support ESN and replay window, all major algorithms. In 1908, we added support for multi-segment packets, and to demonstrate that, we changed IPsec gateway sample application to do fragmentation and reassembly. That's what we have right now, and that's what we're working on for 1911. All patches were submitted. Hopefully that they would end up in 1911. We'll see. So the first one is Security Association Database. That one of the guys in the list of the authors, Vladimir, is our main job force. Second one is driven by Fan, another author who is not here. It's extension for RT security API for software-based crypto device. And the third topic, it's using the same security association over multiple crypto devices. It's changed in the library plus some usage examples in sample application. Okay, so the first part, Security Association Database. So requirements, it should scale up to several millions of sessions. It should be as fast as possible for lookups. It should support incremental updates, and it needs to be RFC compliant. And by RFC compliant, I mean that we need to follow the following rules when we do SH on inbound packets. We need to match the longest aside identifier. So logically, it should look like that. We try to find by, first we try, when the packets come in, we first try to find by SPI, security policy identifier, by destination IP address, and by source IP address. If it matches, great. If it fails, then we should go and find and do lookup now by SPI and destination address only. If that fails too, we have to do lookup by SPI only. So implementation is free to do whatever it wants internally, but from outside world, from external point of view, it should look like that. So keeping this in mind, we come up with the following API. Suppose it's pretty straightforward. First, you create your table, you provide parameters. One of the parameters is usual kind of socket ID, number of entries in the table you want to have, also what type of keys you want to store inside the table, would be IPv6 or IPv4 addresses. And for each, I'll talk about it later probably. Basically, and for each of these things, you can specify what number of entries you want to have. Let's say you envision that majority of your case would be SPI only. So you can say, I want 1 million case for SPI only, and I want only, let's say, additional 100,000 case for SPI plus destination IP address, and another, let's say, just 10K for SPI plus destination plus source IP address. So add and delete and lookup. Lookup is obviously a bulk one to make things faster. Yeah, that's it. Let's go to internals one. So internally, it comprises of 3 hash tables. We use our RT hash. So each table keeps entries for specific key types. So one entry for SPI only, second for SPI plus destination IP address, third one plus SPI plus destination plus source IP address. So obviously in the first key table we have key size just 4 bytes, which is small enough, and lookup would be fast enough. Second one, it depends on IP version. For IPv4 it would be 8 bytes. For IPv6 it would be 16 plus 4, 20 bytes. And for third one, obviously, it would be either 12 bytes or 36 bytes. Okay, and also we have, in addition to that, we have counter array, which is used only for add and lookups. And basically what we store here, we store how many counters we have, how many entries we have in these 2 specific tables. Let's say for SPI 500, do we have any entries in SPI plus destination IP address? If yes, how many entries? Same for SPI plus destination plus source. It is not used by lookup because it's additional, obviously, memory dereference and all these performance issues. But we still need this information at lookup time, right? So the last 2 bits in SPI only table for in entries for SPI only tables are reserved. So they basically represent, they have 2 bits which represent is there an entry in other tables or no, which obviously assumes that that your data have to be 4 bytes aligned. 4 bytes aligned, right, that you put inside this table. Okay, so just some example. Let's say, suppose at first we just doing SAT add for SPI 500, and we want to put it into SPI only table. That's the simplest one. We doing addition into our first table, and that's basically it. We don't have to do anything else. Same for, let's say, next one, we're adding SPI 100, and again, it's only SPI, same thing. But then it becomes a bit more interesting. Now we're adding entry with SPI 100, but also with destination IP. So what we're doing first, we're first going and adding entry to the second table, the blue one, right? Then we go and search for SPI 100 into our first table. Okay, we found it. And we realized that, okay, now we have to indicate that we have an entry with the same SPI in our second table. So we would update this. Before that, this value would just contain, the data would contain just V2 value, right? We have to update the value with V2 and set the 1 bit in the lowest bit set to 1, right? So. And also we need to update our counter array. Then again, we have another add, so now it's SPI 100 and destination IP address and source IP address. Again, we first add entry into our set table because now it's K with 3 fields. Then again, we go and look up in our first table. Okay, found it. We realize that we need to update it. Now the bit fields would be 3, 1 and 1. And we need to update our counter array. Now let's say we're doing lookup. So lookup, all in contrast with add and delete, always starts with the very first table because it's the fastest one, right? And from what I know, majority of use cases is when we have search by SPI only. That's kind of probably 99% of all situations. So when we're doing lookup, we first going to the first table. Okay, we found an entry, but we can't just use it. We realize that we have also entries in our second and third table. So we have to go and do search in both of them. Internally we're doing lookups in bulk and in parallel, but yeah, still we have to do that. We do the search and we found that that entry in second table matches, entry in third table doesn't. So we took our best match, which would be the entry in the second table, so we return value 3. Yeah, so yeah, that's basically, I suppose, gives you an idea. I wouldn't go through the rest of examples. Okay, so some performance data. In addition to the library itself, also Vladimir developed a benchmark tool that could be used to measure performance of this SAD API and these site tables, and also do some functional testing with it. So this is results on Intel Skull Lake. It's 2.1 gigahertz. And yeah, as you can see, it's add some number of entries into the tables. Entries are sort of randomly generated. Then lookup of I think 50 million of times, again through all the entries in random order, and then delete all the entries. So yeah, what probably worth to mention is that performance, well, as you can see, when you increase number of entries, the performance degrades slightly. That you probably all would expect. What is probably more interesting that it depends a lot on distribution of keys inside your table. So let's say in the very right one, right? If you have 90% of your keys just SPI only, just first table, and the rest would be distributed in second and third table 9-to-1, then the performance is, yeah, it's the best one, right? So basically, as more entries you add into the second, you have to add in the second and third table, the worse performance you would have, right? So, yeah, I suppose, yeah, it's pretty clear. Okay, so that's the first topic, the first item we're working on. Second one is addition to RT security API. There, we submitted a patch and there were some comments from Akil about API and all these things. What he suggests is not to put this new API into RT security, but put it into RT crypto instead. I agree, it probably would be more logical and would require less change into existing drivers. The problem, well, the possible problem is that it might cause API breakage. I think we found a way to avoid it, but kind of we are okay now, but if tomorrow we'll have to add some new fields into this session initialization, it might be a problem. So it's, yeah, it's under discussion, which way to choose. Anyway, the main idea remains the same, right? So right now we have CryptoDev API for NQ which is based on CryptoOp, and it creates in terms that it's comprehensive and it's generic and it's totally transparent for users. So you can write your application that would use this CryptoDev API and it would work across all crypto devices that we support now in DPDK, which is really good. But this API was designed for hardware primarily. Software implements it also, but kind of it wasn't designed for software implementation. So, and that adds a lot of extra overhead for software implementation drivers. And we do have quite few of them for for Intel. So, and that's why it's important for us. So basically, yeah, I listed all the things that you have to do, and basically for CPU-based crypto device, you just don't need them. All you need to do is just basically call a function, right? That's it. So based on that, we propose, in addition to existing APIs that would work in synchronous mode, just a function call, all input-output data are passed as function parameters. Right now, when you working, I don't know how many people do use CryptoDev API, but basically it allows you in the same burst to have operations for different sessions, which again is good in terms of that it's generic. You don't have to worry about it, but from the other side, it's not that good in terms of performance because the first thing the driver has to do is to go and check what session it belongs to. While if you would have an API that would accept bursts per session, it would make things much clearer and much easier, right? So sad things, sometimes you don't want to operate on mbuffs. So, and internally, you don't need any information from mbuff except basically the data pointer and the length. That's it. So it operates on raw data buffers. Yeah, so this is proposed API. From IMD perspective, it's a new ops into our RTQ security vector of functions. From user level perspective, it's new action type and new Xform, and then you invoke your usual security init and security create, and then you invoke this function process CPU crypto bulk, which takes, as I said, input data as parameters. As I said below, as I said before, there is ongoing discussion with Akil, so this is probably subject to change. The main idea would hopefully remain the same, but the API might change. We might use this might move it into CryptoDev instead of RT security, which is, yeah, from one side it's easier to do and more logical, but as I said, it might cause API breakage in future. So okay, so what's in the patch we provided, it is this new API is supported by two CryptoDev software back drivers, both Intel ones. It's ISNI GCM and ISNI MB. Also, we added support for this new this new API into IPsec library, and that simplifies adoption of this API, I believe, quite a lot. As I said, we also changed getaway sample application, and yeah, all we have to do is just to change on the data path, just to change 2 lines of code. That's it, basically. Okay, there is some performance for ISNI GCM. So yeah, it's not the actual performance data, it's performance difference with and without this new API. So yeah, it's depending on the CPU, it's 15 to 20%. On Skylake, we think about 15% improvement. On Bordeaux, we think up to 20% improvement. As I understand, the main difference is because Skylake, the editability, they basically increased load and storage size per cycle. They double it. So that's why on Skylake we think a bit less. But this is on Skylake, so again, yeah, what is probably important that in our projections we think that CPU vendors would put more effort in faster crypto operations, crypto instructions on their CPUs. So hopefully the cost of crypto and authentication operation will become less and less. And in that case, this overhead would be much more noticeable in future. Okay. And I think we go to the third topic, and I pass it to Declan.
Tom was just hitting the clock for me, so I'll try and go through this quickly. So some of two of the other things I'll just briefly talk about. We've added the ability to support multiple sessions per essay, and that can be summarized in the value of doing that is that it allows you to have multiple crypto devices or security devices supporting the same essay, and I'll talk why that's some of the use cases. That's really the scenarios where it's useful is. We'll be able to utilize that for load balancing, potentially where you could have multiple crypto devices all processing the same essay when you put in the infrastructure around to handling the ordering issues. The initial element that we're looking at addressing is using this to enable a fallback session. So for inline crypto devices, what we have enabled in this, you have a lot of the devices cannot handle fragmentation of the inbound IPsec packets. So unless the NIC was capable of doing IP reassembly, it's not possible to do the crypto processing inline on the device because you don't have the context there. So in this case, the idea is to create a transparent fallback. So you could have a backup crypto device that's host-based crypto processing. So as the reassembly is done on the host, you've got the majority of packets in the flow have been processed inline, and then when you get that reassembled fragment, you can do the crypto processing on the CPU, and it's transparent for the flow. Also, for the fat tunnel use case, we think this will also be very useful. So if you have a number of worker cores doing processing of the same essay, having an essay, you need a session per device potentially, and that will allow that scaling. So in relation to the inline crypto, as Konstantin mentioned earlier, we have added fragmentation reassembly to the security gateway application, and that allows you to see how the IPsec library can support that use case. So we've registered callbacks on our RX functions and ports to do the reassembly using the reassembly library in DPDK, or the IPfrag library. And this will create a scatter-gather list of the reassembled packet. And then that reassembled packet, the IPsec library, as long as the crypto devices that are utilized in the processing can handle the scatter-gather list from them both, it will do the processing. And then we also have added the ability to support fragmentation and outbound. So if your IPsec tunnel encapsulation causes you to go over the MTU of the device, we will do the IP fragmentation, and it's also useful in testing if you're doing back-to-back setups. You can use that to generate packets to test the actual inbound processing, which is the more performance hitting film. So as I mentioned just on the previous slide, we do have that fallback session in place. So generally what will happen for the inline, you'll create two sessions, one on your inline crypto device, and then a crypto dev device, so either hardware or software, can be used for the fallback crypto session to do the processing as described. So an initial deployment that we have at the moment is a little bit naive. So if you're doing the fallback over a asynchronous crypto device, today, and we will be looking at addressing this, but especially if you're using a hardware offload for the crypto processing, your packet flow in the security gateway can cause reordering of the same flow. So if you had a fragment in your packet flow, once the reassembly happening, then that gets asynchronously pushed to your hardware accelerator, but that means that will come back some X thousands of cycles later in terms of CPU time. So that causes you, in terms of our security gateway application today, you would need to, at the very minimum, address the window sizing to allow for the length of time it takes to dispatch, be processed, and be received from the accelerator. And then you also would have to accept the fact that you've caused some reordering inside the tunnel, which may or may not be an issue. Now, when you're doing the fallback session with the synchronous device with crypto, the synchronous crypto device, you don't need to have, there's no reordering problem, so the packet gets reassembled in the order that they're received on the wire, and you can just do the CPU, the call to the crypto device to do the decryption of that fragmented packet. So you just have the cycle cost. You'll see maybe a change in your jitter for that flow through the device, because you've now, for instance, maybe you've got a 1500 byte packet which costing you 2 cycles per byte to process. So you've added 3000 cycles onto the path through the forwarding path through the CPU. So we are planning on looking at potentially ways of addressing, if you're using the asynchronous offload device, and ways of handling that order, but for the 1911 time frame, that would be an issue there. So I think that covers kind of all of the major updates over the last year.
Very quick.